This chapter is about alpha carbon chemistry, and in particular alpha substitution. So in this video we're going to learn about the haloform reaction, but in order to do that we'll just review that we can add an electrophile to the alpha position. So you can see we've got an alpha carbon here, that is the carbon next door to the carbonyl, and in the case of a base we'll come along with that base, remove the proton, and then the electrons swing down to the carbon. And then we'll have our enolate. So the enolate is because we're in a base. That gives us a carbon minus, or the enolate itself, the enol oxygen minus. But what we'll see is the alpha carbon is the one that's going to pick up our electrophile and add that to substitute for the hydrogen on that alpha carbon. You should also note that this reaction can occur in acid. So in the case of an acid, we'll protonate our carbonyl, and then water is able to remove a neighboring alpha proton from the alpha carbon. Those electrons swing in, pushing them out onto the oxygen, and we'll get our enol. So the enol can do a similar kind of reaction where if I add in an electrophile to that, the electrons swing down from the oxygen and these pi bonds reach out to the electrophile, and we'll get our addition to this position, the alpha position. Still have a plus charge on the oxygen, and the final step will be one of those things can remove that hydrogen to give us our substituted alpha position substituted with an electrophile. So that's alpha substitution with enolates or enols. So now let's go down to the alpha halogenation of ketones. So the same idea is occurring with the alpha halogenation of ketones. So we are going to be able to take a base and a halogen and substitute the hydrogen, that is alpha, on the alpha position with an X. So this reaction, let's start with the base promoted reaction because we need a full equivalent of base. We'll get to the acid version shortly. But first of all, how does that work? Well, our alpha position hydrogen is going to be abstracted by hydroxide, the base. And so that leaves us with our enolate. So you can write a resonance form for that. I'm going to go on and take this one, so plus resonance. So I'm going to use our X. That could be a chlorine or a bromine or an iodine. And we'll pick that up, pushing the electrons to the second X, and that will give us our added or substituted alpha position plus X minus. So this is what happens in our base conditions. So if we consider that that can continue happening, let's just say that we have this CBr. I'm going to just use an actual halogen here, and I have still another molecule of base. That is able to take the next proton, and we'll get another enolate to form. It's actually easier now because of the pull of the electrons from the bromine. And then bromine again will be added to, and so we substitute for another hydrogen in that position. And this can happen again with hydroxide and bromine, and we'll get all of those replaced. So this is what's most likely to happen in base conditions. And it turns out that this thing is somewhat difficult to isolate. So could we have just the right number of equivalents? Well, that's what I applied in I implied in our group work, but probably not. Generally, we don't isolate this. So what happens next is that hydroxide that seems to be hanging around attacks that carbonyl. The electrons swing out. So I'm going to use this as a, this is the next step. But then after that, those electrons swing back, and this is a leaving group that leaves. And so we'll be left with our carboxylate. We'll say this, CBr3 with a minus. And that's going to remove the proton because it's a strong base to the oxygen. And so our final result will be the carboxylate itself and the haloform. So this is bromoform. Interestingly, if we have iodine, I2, that will form iodoform, which precipitates. And that's a Ci3 precipitate with an H, and that is a yellow solid. So that was a test for a methyl ketone. So that's what happens in base. Let's look at what happens in acid for alpha halogenation of a ketone, the alpha position of a ketone. So in this example of acetophenone, we're adding acid. So you can see it's an acetic acid up here. And so in the presence of acid, we go through the enolization process, just like I showed you on the first slide. So here we've formed an enol. And then that enol is going to attack an electrophile. So in the case of alpha halogenation, we're going to have some halogen present. And so those electrons on the enol, which is plus charge, those, oops, no, it's not charged right now. Those electrons will come down and push electrons into the pi bond, which reaches out to pick up the halide and kick off the next halide. And so that will give us our product that is halogenated. So double bond O plus charge, C, Br, H, and H. So this is the alpha halogenated product. So we can add more alpha hydrogens, but there tends to be a slower addition. And so you're more likely to be able to just collect the one halide, especially with one equivalent. So there's our product. So in our example, we've got the cyclohexanone. This would be our alpha halogenated or alpha chlorinated cyclohexanone product. So the way that we would go about this is, again, we're going to take the keto form and add a proton from the acid present. And this is in equilibrium with this resonance form. And in the resonance form, we've got a plus charge on the oxygen, or we can move the electrons up and then we'll have a plus charge on the carbon. So finally, to reach the enol, our conjugate base will take the proton, those electrons swing in, and we get our enol. So the enol then can go on to react with the halogens. So we'd have chlorine here, and we can imagine these electrons come down. These electrons then in the pi bond reach out to pick up the chlorine. And that would give us our chlorinated intermediate. This could be in resonance with a carbon with a plus charge. So there's a resonance for that. And then the final step will be the chloride could take the extra proton and give us our chlorinated alpha position. And we can stop there if we don't have excess chlorine, because the acid catalyzed reaction will allow us to do that. plus HCl.